Ready?
Yeah.
All right. Hi, everyone. My name is Sarah. I'm a graduate student in Material Science and Engineering at MIT.
And my name is Akshay. I'm a graduate student in Electrical Engineering at MIT.
And we're going to talk to you a little bit about the science behind electron diffraction and hopefully convince you that it can also be art. So, to get started, we want everyone to help us with a brief experiment. So what we want you to do is take out your phone and find a partner somewhere in the audience. So you can just sit next to somebody. You need 2 people to do this, and make sure both people have a smartphone. Yeah?
If you don't have a phone, you can join a group where 2 people have one.
Okay. So next, one person just turn off your screen. Just make sure nothing's on the screen. And then the second person is going to shine their flashlight of their phone onto the first person's screen and try to see what you can see in the reflection. And then switch and make sure you both get a chance to look at it. Okay.
So try to observe the reflection of your flashlight on the other person's phone screen. And then once you've seen it and whatever it looks like, you can switch.
If anyone needs help, just let us know.
You can try moving the flashlight forward and backwards just to see what happens. Give them a minute.
Oh, okay. So, just for the sake of time, we just want to go over what you guys saw. Does anyone want to share any observations that they had? Yeah.
Looks like you saw 2 images.
2 images? Okay. 2 images of like the flashlight beam?
Very close together, like 2 instances of it.
Okay. Anybody else? Yeah? Color, you saw rainbow? Mm-hmm. Anyone else?
Other observations?
Yeah.
Well, we found with the glass, it was like some reds and, but here the plastic screen color, they got all like blues and greens.
Cool. Yeah, it's a little bit different if you have the screen color. Did anyone else want to share?
Yeah, like my screen only diffracted horizontally, their screen did it in 4 directions.
Okay. So what do you mean by that? What exactly did you see in one direction versus another?
Yeah, it was a rainbow.
The rainbow.
But it was just in a certain direction.
Okay.
It didn't happen in
Great. So this effect is called diffraction, and this is what we're going to be telling you about today. So you might have seen a larger scale version of this at the beach. Let's say you have waves that are hitting these rocks, but you actually have holes between the rocks, right? It's not a solid wall. And the wave is coming in, and when it gets to these holes, it bends, and it creates multiple waves which interact with each other to form a pattern. And we want to understand what happens when waves overlap with each other so we can see what's happening with this behavior. So as the previous speaker really nicely set up for us, we're actually going to just briefly review it. What happens when you have 2 waves that are called in phase? That means you have the highest point of one wave is matching with the highest point of the other wave, so that when they combine, then they're actually going to add up and produce a bigger wave. This is called constructive overlap because they're adding up together. But you can also have 2 waves that are out of phase, and that means that the highest point of one wave matches the lowest point of the other wave. That way, when you add them up and you take the positive point and add it to the negative point, oops, I think we clicked at the same time. Okay, that's okay, yeah, fine. So then it's going to have destructive overlap because the positive is combining with the negative and you're going to get no light. So we can use these principles to understand what happened when you reflected the light off the phone screen. So first, let's take a look at the phone screen under a microscope. You can see that this looks like a regular array of slits, and actually each of these slits is one of the pixels of your screen. So here, what's happening is when we shine the light on it, it's reflecting off of this array of slits. So we want to understand the behavior of light as it passes through this type of array of slits. So let's first start off with just one slit diffraction. We have our wave coming in, then as it passes through the hole, it's going to bend and create this pattern that you see here. And if we put a screen to kind of collect that light, then we're just going to see a streak on the screen with no features. But what happens when we increase the number of slits? Now we have two slits. We have the wave going through. Now it's splitting it into two different waves, and we have certain regions where they're overlapping, and they can overlap constructively or destructively, as we saw. And then that's going to lead to regions of light intensity and then regions of no light intensity. So if the waves are in phase, then we get an area where we have light. If the waves are out of phase and cancel each other out, we get an area where we don't have any light. And let's keep increasing the number of slits. So here we have 3 slits, and I haven't drawn all the waves, but we're showing what you can see on the screen. And then we're increasing the number of slits. The spots get smaller and smaller. And that's because now we're splitting this wave into many more waves. So in order to have a spot, you have to have many more waves be in phase at the same time. And that's just less likely depending on the more waves that you have. So what we're doing here is essentially splitting one beam of light into many beams of light. And we can get this nice pattern. So this one is just in one dimension. But what you saw on the phone screen, somebody mentioned, you saw this kind of pattern in 2 dimensions. So this is going from a 1D diffraction grating, or a series of slits, to 2D. And then, did anyone see something that kind of looked like this? Yeah? So that's the idea of how it splits into all these spots. And someone also mentioned the colors, and that's also a really good point. So your flashlight of your phone uses white light, and that contains all the different colors of light. And each of those different colors interacts with the slits a little bit differently, so that's how they get split up into the rainbow. So we can make these really fun patterns with our phones, but what is the practical use of this? Well, for one, next time you're playing with your cat with a laser pointer, you can actually reflect the laser pointer off of the phone screen to create a diffraction pattern and see if your cat responds any differently to it. This cat didn't really seem to care, but maybe yours will. Apart from that, there's also some really interesting science that we can do with diffraction. So we talked about the 2D grating, the 2D series of slits on your phone screen. But then what if we make that into a 3D series of holes or slits? That actually is going to look a lot like a crystal of atoms. So many materials, such as metals or salts, for example, table salt, consist of a crystal lattice. That means you have a repeating structure of atoms that's the crystal is made up of. And this can actually act as something that you can diffract light through. So we take light and we pass it through, and then we get a diffraction pattern that looks like this. So this is a really beautiful symmetric pattern, but it also contains a lot of information. We can use the diffraction pattern to understand what the structure of the crystal is, since that's not something we can see with our eyes. So one really famous example actually is the image that was taken in Rosalind Franklin's lab of this X-ray diffraction of DNA. So they used DNA as the thing that they're diffracting light through, and then that produced this pattern. And before people knew what the structure of DNA was, they were able to figure it out based on the diffraction pattern because they knew how to analyze that. And this gives us some really interesting information about the crystal, but one issue is that the crystal is really, really small. And we can't focus light down to become that small of a point that we can probe a specific area of the crystal that we want to look at. The light is kind of hitting through the whole crystal. So there's actually a way that we can get around this and actually probe a specific region of the crystal, and that is by using electrons. So just as a quick reminder, electrons are the negatively charged tiny particles that surround an atom, and we actually can create a very focused beam of electrons. Those electrons can pass through the crystal at a specific area, and we can get this kind of diffraction pattern, which it looks really nice and also contains a lot of information. So Akshay is going to talk to us a little bit more about these kind of diffraction patterns.
Okay, so let me just check if this works. Okay, cool. So Sarah told you guys all about crystals, and so let's look at an actual crystal. So here's the crystal of silicon. So silicon is a very common material. It's found in all of our phones, all of our computers. So if you picked apart one of your phones and took out the chip inside of it and sliced it up and put it under a really powerful microscope, it would look something like this. And I just want to point out the length scale that we're working at here. So you see this number 3 nanometers here. That's telling us how big the features in this image are. And so we're working really at the tiniest of length scales, and each bright dot that you see here is one column of silicon atoms. And so we're able to visualize these atoms directly. But if you look at this image, another thing that you might notice is that it looks very similar to that image of the phone that we had shown you earlier. It's a very regular array of periodic patterns. And so what we can do is take an electron diffraction pattern from this. So we pass electrons through this silicon layer, and this is what we get. Whoops, oops, oops. Skipped a bunch of things.
I think the image is actually not here.
Oh,
It's okay.
how interesting.
Yeah. You can go to the next.
Okay. Our image did not show up. But what we can do is we can pass the electrons through a layer of silicon and get diffraction from it. So we were interested in this process because we wanted to make what's called an interferometer. And very quickly, an interferometer is a device which splits electrons and then recombines them. So we, instead of using one layer of silicon, we use 2. So the first layer split this electron beam, and the second layer re-diffracted all of these diffracted beams and recombined them. And so what does that look like? So here's what that pattern looks like. And so what's going on here is I've taken a diffraction pattern right before the beams have recombined. So you can see that they're all very close to each other, but they've not quite recombined yet. And you can almost see that there's a large diffraction pattern, and then around each of these dots there's a smaller diffraction pattern going on. And that's because I'm getting diffraction from the first layer and from the second layer. And so this is a really nice symmetrical pattern, and it gives us a lot of information about these crystals, the gaps between them, their properties, how even they are, etc. So the second example I want to share with you, oops, let's just skip that. Second example I want to share with you is of thin film diffraction. So in my lab, a lot of people are working on making detectors for light. So materials which, if you shine light on them, they'll respond in some way, so you can drive other applications from it. And one of the materials that they work with is called molybdenum silicide, and they grow these thin films of molybdenum silicide, and they want to know what their properties are. What do they look like? What is their crystallinity, etc. So one of my colleagues grew this image, and then he wanted to know more about it. So we put it under a really powerful microscope, and this is what it looked like. So again, I want to draw your attention to the scale bar here. So not quite the same level as the previous one, but we're still seeing these very small details. And you can see that the layer has some wrinkles going on, there's some features, but overall it's a pretty boring image. It's gray, it's gray everywhere, there's some shapes and lines, but there's not a lot of information that this image gives us about this crystal. So we wanted to get more information, and so we took an electron diffraction pattern from it. So we passed electrons through this image, and we wanted to see what came out the other side. And this is what it looks like. So far you've seen these regular array of points as diffraction patterns. So here what you're seeing is these rings, right? So 1 ring, 2 ring, 3 rings. This actually has like 6 rings, but they don't show up very clearly. So what this tells us immediately is that instead of being one large crystal like that silicon was, our material is made up of many tiny little crystals. So each tiny little piece of crystal contributes one of these little points that you see here, so like that point or that point. And then because there are so many crystals and they're all arranged in different ways, they all combine to give us these rings. And so that immediately tells us something about the structure of our material. The other very interesting that you can do with electron diffraction is, instead of using all of these electrons, so right now I'm forming this diffraction pattern, I'm using all of the electrons that this layer gives me, I can block out some of them. So I can block out all of them except for a very small fraction here. So So let me just repeat that. I can block everything all of the electrons in this image except for these electrons. And then I can look at only the parts of the image that give me these electrons. And so when I do that, this is what the image looks like. So this gives me a lot more detail about my material. It immediately tells me what the size of these crystals is, how they're arranged, how frequent they are. So for example, one of the really useful pieces of information for my colleague was that each of these crystals is something like 50 to 100 nanometers big, so he can begin to understand more about his growth process. And I think that it's a really cool image. The contrast between the background, which is all of the parts of the layer which we blocked out, and the bright points, which is all of the parts of the layer whose electrons we let through, I think that really stands out.
Yeah, so I don't know about you guys, but I can definitely see this hanging up in a hotel lobby somewhere. So we hope that we've convinced you that electron diffraction is the future of modern art. And if you're interested in taking a look at some more of these kind of images, you can follow us on our social media. So you can follow Akshay on his Instagram, and you can follow my YouTube channel, where I show some of the lab experiments of how we actually get these images. So thank you so much.
So I know a lot of your diffractions, most of your diffractions are two-dimensional. Have you guys experimented with three-dimensional diffractions? Like, because you said that you shot electrons through your crystals. What if you had your electron source inside the crystal and you shot it outwards and then had them within a medium that could capture the light? Could you possibly create images that are three-dimensional, and then by changing the structure of the crystals, change the image in such a way that
Yeah. So actually, these images, so it's an image like this or an image like this, oops, it does give us three-dimensional information about our crystal, because what we're doing is, these kind of crystals that I showed you, they do have a thickness to them. And so when we shine electrons through them, the electrons go through the entire thickness, and we look at what comes out on the other side. So they do give us three-dimensional information about our material. If you want to get more three-dimensional information, there are ways that you can tilt this crystal. So instead of just it being like this and the electrons hitting it down, you can tilt it, you can rotate it, and so that you can, so there's a technique called electron tomography, which lets you reconstruct the whole 3D structure of the crystal by doing all of these tricks. So you can get complete 3D information.
Yeah?
Are you doing anything with UVC LEDs? Or is it mostly art? UVC LEDs that kill bugs?
Oh, I mean, me personally, I'm not, but I think you could, I'm not sure if I completely understand your question, but I think you could use, depending on the wavelength of light you use, you'll get a different kind of pattern. And so if you were to use this kind of light, I guess it wouldn't be in the visible, so we wouldn't be able to see it. But you could potentially use whatever wavelength that you wanted. Do you have anything to add? Okay. Anyone else? Great. Let's thank our last speakers.